Hello and welcome back. So in the previous sessions, we looked at how to solve very simple problems using finite elements. So we looked at very simple Laplace or diffusion kind of problems, and we really developed this from scratch. So we developed the shape functions, whether they were triangles or chords, or they were bricks or tetrahedrons. So we developed them from scratch. We built meshes in Gmesh, and we also looked at the mesh quality, how to decide the mesh quality, and how to really do the meshing and read the mesh and develop a solver from scratch in MATLAB, Julia or Python. And these very simple diffusion problems were really good test case for understanding all of those basics. And of course we also put different kind of boundary conditions like Robin conditions, and towards the end we looked at a very simple workflow in Phoenix for solving these diffusion problems. We also looked at how we can use the SLEP-C, which is your eigenvalue solver. So really beyond this I wanted to go towards Navier Stokes, and sadly due to lack of time I am not able to develop a bunch of videos as detailed as the previous one. Nevertheless, I will start off with this laminar incompressible flow walkthrough, and then we could go towards turbulent flows. Towards the end of this walkthrough, obviously I will motivate the turbulent flows. I will show a very simple code for that, and then we could go towards turbulent flows and multi-phase flows. So of course for this bunch of videos, to be able to understand these, it's important that you know the basics of your fluid physics. So it's good if you have taken a course in fluid dynamics, without which it would be very difficult to understand what's going on in these videos. And so this is the walkthrough structure. So first we'll just look at the pressure velocity formulation, and then we'll go towards the Stokes flow. Of course we have to understand in the first part, in the pressure velocity formulation, the concept of pressure as the Lagrange multiplier, and we also have to understand the inf sup or the LBB conditions, without which we cannot get stable and convergent solutions. So I have really tried to keep it very simple because this is more like a walkthrough rather than a course structure. So I have really provided some codes to probably simplify the understanding of these concepts. And after this we would go to the Stokes flow, where we'll see how to circumvent the inf sup conditions by using Petrov-Galerkin method, which is very commonly used. It's called as pressure stabilized Petrov-Galerkin. And then we would go towards the laminar flows with higher and higher convections, which would of course need stabilization again, because our Galerkin scheme is more like a central difference scheme. So it's not good at handling hyperbolic equations. And as your convection starts increasing, your equation becomes hyperbolic. So we have already seen this in the previous bunch of videos on 1D codes, where we looked at the streamline upwind Petrov-Galerkin for a convection diffusion problem. So now we'll just use the same thought process on Navier Stokes, and I'll also provide the codes for both of these, and this would probably make it easy to visualize. So we'll see our problem, which wasn't converging without SUPG, will converge once you have put SUPG into picture, and we'll also show some of the validated results against that. So we'll just look at the lid driven cavity in this particular walkthrough, because very simple and straightforward problem. Of course towards the end we'll also look at a comparison between the Taylor-Hood elements, P2 P1 kind of elements. It's called as a Taylor-Hood pair, which is stable and it satisfies the inf sup condition, and we'll compare this with P1 as well, and hopefully that will just bring about a nice visualization of how to solve basic Navier Stokes flows using finite elements. And we'll end with a simple visualization of a RANS kind of model in finite elements, of course. So very simple visualization, and that would segue into the next bunch of videos, where we can look at more advanced turbulence concepts. So so that's what I wanted to talk about in this introduction. And so in the next video, let's just start off with the introduction.